So what is an algorithm? What is a program? And what is a programming language? So an algorithm is an unambiguous step-by-step procedure to produce some result. The word algorithm comes from the name of Persian mathematician Muhammad ibn Musa al-Khwarizmi, who lived around the year 800. He wrote a book, the compendious book on calculation by restoration and balancing, which described a procedure for solving linear and quadratic equations. The word restoration in the book's title, al-Jabr in Arabic, also gave us the word algebra. So we often think of algorithms as being related to computers somehow, but they're much more general than that, whether it's solving quadratic equations or adding two numbers by hand, or following the instructions lather, rinse, repeat if necessary on a shampoo bottle. We perform algorithms all the time, even in the absence of computers. When we, as engineers, provide instructions on how to implement a process or build a structure or a machine that we've designed, we're expressing an algorithm. And when we solve a problem, we want to think algorithmically by clearly defining and stating the steps needed. Algorithmic thinking is an important and fundamental skill, not just for computer scientists, but for engineers of all disciplines. So then what are programs? So they are what tie together algorithms and computers. A computer program is a collection of instructions that tell a computer precisely how to carry out an algorithm. Programming, then, is the process of providing those instructions or of translating an algorithm, step-by-step procedure, into a program, a sequence of instructions that a computer can understand. So if we want to tell a computer what to do, we have to speak a language that it understands. That is, we have to use a programming language, a formal language designed to communicate instructions to a computer. Formal here means that the language follows precise rules, so we can tell exactly what a program is going to do. There are thousands of programming languages out there, of which dozens, maybe even hundreds, are in regular day-to-day use. A professional programmer will usually learn several programming languages, choosing the right tool for each job. Programming languages can be classified in a number of ways. The first is low-level versus high-level languages. Low here means closer to the language the computer speaks, and high means closer to the way a human would express an algorithm. Low-level languages include machine code, a sequence of numbers that a computer's central processing unit treats as instructions and can follow directly, and assembly code, a more human-readable version of machine code. A single machine code instruction does very little by itself, maybe adding two numbers, or storing a number in the computer's memory, or jumping to another instruction. Every different type of processor has its own languages for machine and assembly code. The Intel or AMD processor in your laptop has one machine code, actually two for 32 and 64-bit programs. The ARM processor in your phone or tablet has another, and the Atmel processor inside the Arduino has another. For many years, machine code and assembly code were the only way to write programs. But unfortunately, machine code is difficult to learn, verbose, error-prone, and machine-specific. High-level languages were introduced, beginning in the 1950s, as a more human-friendly way of writing programs. So high-level programming languages include Fortran, the original high-level language, C++, MATLAB, and many, many others. So in a high-level language, a single statement might stand for several machine code instructions, perhaps even thousands of instructions. Furthermore, a program in a high-level language can be made to run on many different computer architectures. So we say that high-level languages are portable. High-level languages are very nice and are how the vast majority of programs are written, but the computer's hardware only understands machine code. So if we want to write our program in a high-level language, we have to translate it into machine code somehow. There are two general ways to do this, with an interpreter or with a compiler. An interpreter reads and executes code directly, translating as it goes. On the other hand, a compiler translates the code without executing it. The translated version of the code, usually machine code, can then be executed over and over again. Some languages, such as JavaScript, Python, and MATLAB, typically use an interpreter. Others, such as Fortran, Pascal, and C++, typically use a compiler. Still other languages like Java lie somewhere in between. The Java compiler translates code into an intermediate form that's later interpreted by the Java virtual machine. There are advantages and disadvantages to each method. Interpreters make it easy to change a program. You can simply edit the program and then run it again. Since the code is translated each time the program runs, there's no need to do any additional steps in between. On the other hand, with a compiler, changing the code requires a separate translation step called compilation before you can run the updated program. But this strength of interpreters is also their weakness. Since instructions have to be translated every time the program runs, interpreted languages are usually slower than compiled languages. Furthermore, the user who runs the program needs a copy of the interpreter, whereas compilers usually produce code that can be executed directly by the CPU and the operating system. Only the programmer needs a compiler. So an analogy from the real world. Suppose you want to make baklava, a kind of Turkish-Greek dessert pastry. You have a recipe handwritten by the chef at your favorite Greek restaurant, but unfortunately it's written in Greek, which you don't understand. Fortunately, you have a friend who speaks both Greek and English, but your friend is really terrible at baking, and if you let them even touch an oven, they would surely burn down the building. So what do? You could have your friend stand with you in the kitchen, reading the Greek recipe and telling you the instructions one at a time in English. Then your friend is acting as an interpreter. Alternatively, you could give your friend a copy of the recipe. Then, in the safety of their oven-free dorm room, friend translates the recipe into an English recipe and hands it back to you. Your friend is acting as a compiler. So you can get it started more quickly with the interpreter, and if the chef makes changes to the recipe, maybe replacing the walnuts with pistachios, that's no problem. Your friend will tell you what the changes mean. However, the compiler will allow you to make baklava more quickly in the long run, since you don't have to wait for a translation at every step, and you will be able to make the baklava on your own, keeping your clumsy friend well away from the kitchen.